Okay, for some reason this thing's cutting off the top of the board. Cuts me off. That's to everybody's advantage. If it cuts off the top of the board. Okay, so we have, first of all, the definition of the divergence of F. It implicitly by the definition I give it. Del dot F. And that's done in a very straightforward manner. Okay. So, example, if here's your function, x squared I plus 2y squared j plus square root of g square root of zk, then divergence of F, and I don't know why I put an arrow divergence, scalar, equals F equals partial with respect to x of I plus a partial with respect to y plus a partial with respect to z times k, dotted with x squared I plus 2y squared j plus the square root of b k. And that equals I dot I is 1, so you take the partial with respect to x of x squared. Now, this is not really a dot product because a dot product is defined between two vectors. And the partial with respect to x is not a number. Okay? But we still treat it as if it's a number, and we call this a vector operator. And it acts just like, it feels almost exactly like just plain old dot product. In other words, I dot I is 1, so we do partial with respect to x of x squared, and partial with respect to y of 2y squared, plus partial with respect to z of the square root of z. Put that equals 2x y plus 1 over 2 square root of z. Be careful to exclude z equals 0 from the domain. So this would apply to this function everywhere in space except at the z-axis. And that's because the square root function has a slope that approaches infinity as z approaches 0. So if you drew this vector field, it would get very, very steep as you approach the z-axis. The vectors would get very, very big as you approach the z-axis. Okay. Deal about divergence. Well, divergence is really kind of related to flux. Okay. So I'll just say this is related to flux. I'll say no divergence no divergence at a point implies there's no flux through a tiny region about the point. And if there's zero divergence in a region, it means there's no flux through the boundary of the region. Okay, so So it's not a real specific statement at this point. We'll make it more specific. This means if you have zero divergence and in some closed region of space, there's no flux of that vector field. Okay. Now, you know, need more words to give you a rigorous definition of that, but that's the idea. Also, since everybody in the class is new to physics, if you don't have any charge within a region, then there's no flux of the electric field through that region. And also you can talk about the net flux of a magnetic field. A magnetic field is actually a curl, and we're going to get a result related to that. Okay, so that just kind of put it in context. Divergence is related to flux, and the last section, last topic in the class that we'll be getting to by the end of the month is the divergence theorem, which is basically Gauss's theorem. And it says that if you integrate the flux throughout the region, I'm sorry, if you integrate the divergence throughout the region, you get the flux. Matter of fact, I'll state that right now too. Integrate divergence of L through a closed region, you get the total flux through the boundary. And that's a divergence thing. Now we need to develop some ideas around the divergence theorem, but that's the general idea. And again, that should be familiar to everybody. Well, actually, not everybody, because we do have, matter of fact, I'm thinking of the physics class. Not everybody here has been through the physics, I think. Not everybody that's in this class. Since people who aren't taking physics or haven't taken it are not here today, I'm a little bit out of it. See what I did to my hand? It's just a little cut in the webbing between my little finger and the one next to it. But I've got to immobilize 3 fingers to keep it from splitting apart. So that's a pain. Down to my index finger. Fortunately, I got my index finger. Okay. Just in case you're just, and the reason for that, minor little thing. It might take forever to heal. Okay, get the idea? Now, everybody has seen the idea of flux because that's been mentioned in previous sections. So it's related to divergence in a way that will tease out as we move along. Okay. Now, Earl. Beth is calculated as del cross F. So we can say that the same function we have here would usually use the determinant. Although if you're missing components, you can always shortcut the thing a little bit. Okay. And just use a distribute form. Okay. Well, then this is I times I times the partial with respect to y of z squared plus a partial z with respect partial with respect to z of y squared. Okay. Well, turns out that that's the I component 0, and it's going to turn out that all the components are 0 because the I, J, and K components of F involve only respectively X, Y, and Z. And in every case, you're going to be taking a partial with respect to a different variable. So all these come out 0. Now, hopefully you can see that at a glance, but let's write it out. And, my function isn't x squared, y squared, z squared. It's x 2y squared. And it's the square root of z. So let's fix that. That should be the square root of z. This should be 2y squared. So we're going to have the partial respect x of square root of z. Write it all out, and we find out that all our partial derivatives are 0. So we get the 0 vector. And field is source free. If there ain't no divergence. That is, if the divergence is always equal to 0. It's like you don't have any charge in a region, so you don't have any electric field. Okay. Specifically, we'll have seen this form of Green's theorem. The form we derived last time said if you do the integral of f dot t ds, that's equal to the double integral of dy minus dx with respect to area. The difference in these two pictures, if you just look at a rectangle, integrating around the rectangle, and so backwards here. The field is pi plus qj, and I'm looking at the wrong thing here. The reason you get a net integral along this path combined with this path, in other words, along your two horizontal paths, is because p changes with respect to y. Okay. And the reason you get a net integral over these two paths is because q changes with respect to x. Okay. When you go to looking at the normal component of the integral, then you're looking at I think I'll say, and it's like you're doing qi minus pj. Qi minus pj is perpendicular to pi plus qj. Okay. And when you do qi minus pj, q takes the place of p, so you're going to get qy, and p takes the place of q, so you're going to get minus negative px, which is what gives you this. Okay. I don't want to go into too much detail on that until you digest it a little bit, then we can draw it out and make it really explicit. So the reason I mentioned this is report here. Okay. Right in the assumption, if I don't have any pain here, it's because I'm not trying to pull the thing apart. Okay. So I'm just trying to avoid pain, not that it hurts that badly, but healing. So, okay. If consider f of xy equals negative yi plus xj. Circulates like this. Not doing a very good job. This should be surface centered at the origin. So let me move my origin over a little bit. Okay. Why is it like this? It's because this vector is going to have the negative reciprocal slope of xi plus yj. If I dot this with xi plus yj, I'm going to get negative xy plus xy. Meaning that it's perpendicular to the radial vector because xi plus yj is radial. Okay. So if the field is like this is perpendicular to the radial because all your radial vectors are along these lines and all these vectors are perpendicular to them. So that's a circulating field and it doesn't produce any flux through a surface. At least it certainly doesn't produce a flux through a circle concentric with the origin because the field is always parallel to the origin, to the curve. So you have no field penetrating that curve. Okay, so there's no flux. And it can go a little further than that. If you let never mind. Just stick with this idea. So you got a rotational field and you're not getting any flux through that curve. And similarly, you're not going to get a flux through the surface. Okay? This function f of xy could be represented by a function f of xy z with the z component being 0. Okay, so we'd say that's an f of xy z curve. I have a 0 k. In that case, the curl of this thing is what? It's I times partial with respect to z of negative y minus partial with respect to x of 0. And of course, that's 0 I. and it's plus j times the partial with respect to y of 0 minus the partial. Got a wrong partial here. Three partials y. And that's, I don't know what I'm doing. I mean, this hand is distracting me a little bit, but very little. It's I times the partial with respect to y of 0 minus the partial with respect to z of negative y plus j times partial with respect to y of 0. And it isn't, it's partial with respect to z of negative y. I don't know how I'm looking at this, okay? And then minus partial with respect to x of 0 and pay dirt. Well, we hit pay dirt on k. When we do k, we have the partial with respect to x minus partial with respect to y of negative y giving us 2k. Both of these, everything here and here gives us 0. What we got here gives us 2. Okay. Now think about it. Right-hand rule. You're circulating around this way. Your cross product is in the positive z direction, right? That's a positive circulation. Some of you are very familiar with that physics because you use the right-hand rule a lot there, the circuits and so forth. Okay. So, that's calculation of curl F of that rotational field. Notice when I told you what the curl was, I was careful to say, this is how you can calculate the curl, okay? The definition of the curl is just what you get here. It's all written out linearly, okay? And the two are equivalent, but there is a reason for the definition. It goes back to the distributive law and what it tells you component by component. But I'm not going to belabor that because nobody ever remembers it anyway. Okay, you can rearrange, and I gave you some indication, kind of vague, of how that is done. Now, when I say F dot N ds, that's the same as dot dr, same thing. This is saying it's a circulation of the field, integral of F with respect to dr, okay? In other words, you're going around this circle, your R is changing from here to here, your dr is in the direction, it's a tangent direction, and you, I hope you're real familiar with that from what we did in the first few chapters, okay? So the integral of F dot dr is just a tangential component of the field, and the tangential component of the field is always parallel to the field. So it's just like you're summing up the values, magnitudes of these vectors around the circle with respect to distance around the circle and all that stuff. Okay. It tells, the theorem says that, well, the curl of F is just 2K, right? So for this example, the integral of F dot dr for this function is just 2 times the area of the circle enclosed by the circulation. Okay? Because why? The curl of F we found to be 2K. So curl of F dot K is 2K dot K, which is just 2. So you got 2 times the integral of the area increment. Pull out the 2, you just have the integral of the area increment, which is its little area. Okay? So that's 2 times the area. We could verify that. I'm not going to take the time to do it. But on the unit circle, integral should be 2 pi. Because the area of the unit circle is pi. And you can set up that integral. Just parameterize the curve. In other words, let x equal cosine t, y equals sine t, so that dr equals negative sine ti plus cosine tj. And you dot that with negative yi plus xj. Well, that would be, y would be the sine, so it'd be negative sine ti, right? And you dot that with negative sine ti, you get sine squared. Okay? And xj, x would be cosine t. You dot that with the j component here. Okay? Then you'd integrate that for t from 0 to 2 pi. But of course, you're getting sine squared plus cosine squared, which is just 1. Which makes me wonder, that's just the area of the circle. It's not 2 times the area of the circle. So that's a WTF situation. And just meaning, what's this functions? Curl of F is definitely 2. Well, anyhow. What it should be, because it is diversing in P and Q. I don't want to take the time to write it out, but very possible I did something really simple. and overlook something. What I got for not writing it out, it just all of a sudden hit me that, this is an integral around the boundary, which has a length of 2 pi r. Okay, so when you do this integral, you get 2 pi r times the constant value of sine squared plus cosine, which is 2 pi r. And today, I guess. I thought I slept pretty well last night. Hand was aching just a little bit. That didn't seem to bother me. So I don't think I have an excuse. Okay. In fact, I'm going to do it right now. Okay. We've got this example that says the spin of a gravitational field is 0. That's great. It's an important characteristic. And it's a direct consequence of the fact that the curl of a gradient is 0. If you know about gravitational fields, which some of the class does, you know that gravitational field can be derived from a potential field. The same is true for an electric field. Okay. I'm going to do the general thing here. That's always good to do. It's not that hard, but it is good for your soul to see the symbols and see that all you have to do is keep your wits about you and do the symbols, and any fool can do it. Okay. Just make sure you can do it if it gets asked on the exam. Okay. So what I want to say is, zero. Intuitively, what that can be taken to mean is that, excuse me, better with the camera picture. Intuitively, what this can be taken to mean is the divergent measures how much stuff is flowing out of a point. And of course, it's true at every point, so the divergence can be pretty crazy. Okay. Not the divergence, the gradient. Can't do the curl, the divergence, because the divergence is a vector. And it's a vector that points in the, well, so we'll get to that. So this means that del del F always has to be 0, or F is some function. Del cross fxi plus fyj plus fzk is always 0 vector. Let's be careful about that. Well, what's that mean? That means I, j, k the fx, fy, fz has to be the 0 vector. Well, how do we prove that? We just go through all this and write it out. And if we write it out, it's very straightforward. And I hope it works out for the thing. Okay. Look at what happens on I. You're doing partial of FC with respect to Y. And partial of Fy with respect to Z. Well, the order of your differentiation makes no difference. Those are equal. Then it's J times what? Partial FZX minus FXZ plus K times F. Careful to get it right. FYX. And that's clearly every factor is zero. Okay. I'm sure they mention this a little later in the section. Now, when they say that gravitational field is irritation, that is, curl of the gravitational field is identically a zero vector. Since if you know the physics, gravitational field is just the divergence or the gradient of the potential function. Okay, we determined the potential function. This function is just times your radial vector. I think so. That's potential energy function. The potential energy per unit of mass. And I'm just mentioning this, if you haven't had physics, you wouldn't necessarily relate to that. If you have had physics and don't relate to it, you ought to review gravitational potential energy and not MGH, the big G big M over R. It's actually big G big M little m over R, but since it's per unit mass, that little m cancels out. So wouldn't be a bad idea, both for understanding what we're doing here in this course and making sure you understand the important physics. It's also important for electricity and magnetism, which we were taking right now in the second semester of the university physics course. Okay. Okay. Class, we got the question. Okay. Is a curl a vector? Well, yeah, I've always written it as a vector. Okay. I think. Even when it's zero, it's the zero vector. Because you have an I, a J, and a K component when you do the curl. So curl. The vector. So it could possibly be the zero vector, but that's still a vector. Okay, divergence. Scalar, and the confusion comes about because the gradient this is a vector. Just take any scalar and take the gradient. Okay. Make sense? And take any vector and dot it with del. The I gets dotted with I, the J gets dotted with J, the K gets dotted with K, they become scalars. Okay. Then the curl works out the way we just said. Okay, now I think, again, I'm trying to stay with the order of the text. Just partly to be sure I don't forget anything. But I think the next thing is going to be what I just. Curl is a circulating thing. Divergence is something that comes out radially, okay? In all cases, the divergence of the curl is always zero. Now, that is shown the same way this was, okay? It's a little more complicated, but you've got a vector function to take the curl of, and then you take the divergence of that, okay? And I'm just going to start writing that out. I'm not going to write the whole thing out, but that's partial with respect to x, I, plus partial with respect to y, j, plus partial with respect to z, k, dot, I, j, k, p, q, r, let f equal pi plus qj plus rk. I think those are the letters the book uses. And I'm so such a hurry to get those. Now, first we got to do partial with respect to x, partial with respect to y, partial with respect to z, then p, q, r. It gets a little complicated, okay? And there are more terms than there are here. But if you keep your wits about you, carefully write out what this gives you and then dot it with this thing, you see everything cancels out again. And I thought it was pretty cool first time I did that. Okay. So man, you prove this mysterious thing. Of course, when I took it, nobody ever mentioned what these things mean. Because we were in the Bourbaki school, Bourbaki. Bourbaki. And I think I've lost my ability to pronounce it. Bourbaki. Yeah, our department was big on that, which means you just did mathematics as a bunch of symbols without meaning. I'm probably oversimplifying it. And that was great. I learned to do things very abstractly. But I'm really, when I did, I usually figured out how to motivate it with something I could understand. Okay. So, so when I saw this proof, I was thinking circulations and stuff, but I hadn't put it all together because nobody talked about that. Okay. Uh, when I saw the proof come out, that was kind of a revelation how easy it was to prove. Okay. So it's very easy to do something on paper without understanding a bit of what it means. And I kind of tend to push meaning. Field is zero. Why? Well, because a conservative field, the gradient of a potential function, we just showed that the curl of a gradient is zero, identically zero. Okay. Now, a question, is that an if and only if statement? Leave that for maybe some of the problem. Okay, the idea of the divergence of a gradient. There's a gradient, there's its divergence. So you can write out what that is. The gradient is fxi plus fyj plus fzk. The del operator is here, and you dot it, and what do you get? You get this. Okay. And you define that as del squared F. Any function, well, the functions that satisfy this equation if this del squared, if the gradient of the divergence is everywhere zero, then the function is said to be harmonic. And don't get me started on that. We'll get into complex variables deeper than you want to think about it. Okay. And the example the book gives is if there's no charge in a region of space, then the electric field is harmonic. No, there's a lot more. And
Is that kind of how superconductors work?
somebody in the hall talking to us. Let me